sure we don't know each other.
Hey, David, you want to join your team? Because you should know your team number or my email.
Yeah.
Yeah, so go join your team and introduce yourself to your team. So this way you all know each other. Okay, and another thing is I'd like to encourage you to print out my lecture notes. So here, as the first, this is like an offer. I hope that you will get hooked to this, that you can easily follow and write your notes, okay, on the hard copy. And every student is allowed to print freely 250 pages a semester, so why not make use of that? And when I was doing the photocopy, I was thinking, well, actually, I use a large font size. So, in fact, I can print, I need to find a way, I don't know now how to do that yet, but 2 pages on one, so it's like 2 pages, so that saves more trees. So please come and pick up, and if your teammates are not here, keep for your teammates because I don't want to carry this back.
Which one of you guys need to copy?
So I have here 50 copies. Okay, so
Pretty much everybody?
Just for everyone. Actually 51 copies. You know your team number? Yeah. Yeah, so you may want to, yeah.
I'm not responsible for that, I'm just old.
Actually, you can send a representative and pick up a stack for your team mates, right? You don't need to everyone to come up here. Maybe Jackie, did you get one copy? Yeah. Just pick up for your teammates, and if anyone is not here, keep a copy for your teammate, so you can pass on to that person. Okay, so please, there's still a few more copies here. Okay, like I said, keep for your teammates. You should know how many in your team. 6 to 7. Okay. Let's see. So that's. And yesterday, Michael informed me that of this link here. Let me bring up the mask. To focus on today's lecture. Yeah, please join your team. Yeah, there's a hard copy of my lecture notes to encourage you to print out a hard copy.
Thank you.
You should know your team number and join your. Okay, so for those who just came, you should know your team number, and here is where your team is located. So go join your team. Okay. You can look at see where your team is sitting. Go introduce yourself to your teammates. Okay. Yeah, so Michael informed me that from this link here, UF Printing Lab, every student has 250 free copies that you can print out, and if you save, you can print 2 PDF pages on one hard copy pages, or even 4 on one. So that saves a lot of papers. You can print out all of my lecture notes. They're pretty stable now. And even if I make any updates, you can always, note down by hand or just print out that particular page. And the scanners are in the Marston Science Library. Also, you can use if you don't have a scanner. Okay, so that's now let's. I could have put here my handwritten notes from last time, meeting 3, and you can see that I have added my annotation to what I said last time. Okay, so let's see. But it's easier actually if I bring this up using Sumatra PDF. So let me get it just larger and easier to. Oh, I think I already have it here. Okay, so yeah, zoom out so that you have the big picture. Yeah, so that's my annotation, and this is what we did to show why you add the two forces, the spring force and the damper force. Okay. Now, I did also mention that you cannot do this addition of the forces when you have the spring and the dashpot or the damper in series. Why? Maybe this is a good critical thinking question here before we move on. In fact, if you read carefully my notes, the hints is written on the wall. You know, the answer is written on the wall. So just contribute. The answer is written there. The van.
Is it because the spring force is going to be equal to the damping force?
Spring force is
Equal to the damping force?
equal to the damping force. Right, yeah. So if it's in series, so let me bring up my handwritten notes for today. So if we talk about system in series, and so I already prepared this one. Okay, and then you turn off small ink. And zoom in a little. Okay, so if you have a spring in series with a damper, viscous damper, right? Then one can no longer add, because like Devang was saying, if you do Euler cut, isolate the two elements, you know, the spring and the dashboard. Okay. When you perform a cut, first, you know, so here is a free system, right? So there would be, you can put the forces, and let me do like this. Okay, you can think of that as reaction force, and I do things that, unlike what you learn in statics, in the sense that all of the directions are assumed in the positive direction. Okay, and this is what you do in finite element. So this is in preparation for finite element directly, well before you take that course. Okay, so everything is in the positive direction. So these are algebraic quantities. So that means that when you solve the problem, if the result is negative, it just means that the initially assumed direction is just reverted. That's all. So initially we assume, you know, uniformly that everything is in the positive direction. So here you can do the same. Okay, so let me draw this. But here I can also put in the positive direction, but we know by action and reaction, the two forces would be equal and cancel, okay, in magnitude. So here if you have F sub C, you have F sub C here, and if this is F sub K, right, over here, you know, you should have minus F sub K, so that the sum, you know, if you look at the equilibrium of the spring, right, the sum of the two forces must be equal to 0. That's why I said that. You know, this is algebraic, and this is more like statics here, where the direction is implied in the direction of the arrows. Okay, so from here, just by looking at you know, at this part here, okay, you have f k minus f sub c equal to 0, right? So therefore, f, the spring force, is equal to the damper force. Okay, but is that all? Is that all? How about the displacement? You know, the stretch in the spring and the stretch in the damper. What do you do with that? You know, let's review the case of the of this case where you have the spring and the damper in parallel. What were equal and what had to be added? So clearly, there the contribution. What were equal, Kevin?
Well, FB is equal to FK plus FC. Is that what you're talking about?
Yeah, you know, so this is the sum of the forces equal to 0, and we concluded that you know, the force FB belonging to element 1 is the sum of these two forces. Okay, so that's, but okay, my question is, what are equal? So we already summed this. Yes.
FB is equal to minus FA.
FB equal to minus FA. Let me start to remember your name here. So first, before I forget, the van, what team number?
6.
So this is how I identify you. So no last name. So that's why it's preserve your privacy. And Kevin, what team number?
7.
Kevin?
7.
Team 7. And what's your name?
Jason.
Jason. What team number?
8.
Team 8. Okay, Jason, you said I'll come to you. Yeah, I'll come to you soon. What did you say again? You said F. Can you repeat what you said?
FB is equal to minus FA.
FB equal to minus FA. You mean if you cut this part? Okay. Yeah. But what I'm, you know, remember there's force and displacement, right? So maybe yes.
The displacement is
Very good. Yeah. You know, so here in this picture here, the displacement or the stretch of the spring and the stretch of the damper are the same. They are equal. And what you add were the forces. Okay? Now, when the two are in series, then you have the other way around. That's really, you know, so when the two elements, the spring and the damper, are in series, then the forces are the same, but you need to add the displacement. That's really what I was going at. And so here, one can say that, you know, if you define, okay, maybe let me write here, say dk is displacement in the spring. The subscript k is just mnemonic for the spring constant k. So, and likewise, the subscript c is the displacement in the damper. And the total displacement is the sum of both. Okay, so total displacement, maybe you can write like this. Okay. Then is dk plus ec. It's getting more and more complex, but I just want you to really keep in mind the difference. All right, any questions on this? Feel free to come back if you have further questions as we move forward. All right. And so I'd like to continue this. Let me give a small quiz. Just take 1 minute to do. You can talk to your teammates as well. And this is just to as a guise of reviewing what we did last time, right? So suppose we have a spring and a damper in parallel. Okay. And let's call this an A, or node A and node B here. And you have the internal forces. As you see, it's all in the positive direction. And so this is, and let's say this is element 1 or element 2 or element 3. Doesn't matter. This is not directly related to the example, but let's make it element 1 so that you can follow what is going on here. So this is K1 and C1, right? So therefore this is F sub A of element 1, the force at A of element 1, and this is the force at B of element 1. And now if I put in the numbers and ask you to obtain the force displacement relation, okay, so let's just any number, doesn't matter. Let's say this is 5 and this is just different, 2. Okay, so find the force. What is the force? Find the force displacement relation. Okay, this is an acronym that I often use to designate force displacement relation, which is in my lecture notes as well. Right, so think about it, discuss, and come up with the expression. This is like an exercise, okay, with numbers so that you can discuss with your team. It's not too long. The formula is even in my lecture notes. You have my lecture notes. It's just to connect you from the abstract variable to the more concrete numbers. That's all that is. In matrix form. I'd like to have the force displacement relation in matrix form. Anyone who see it, just raise your hand so we move forward. Give the answer. So let me start so that you can sort of see where we are heading. So if you put so that's already a hint there. Can you complete the sentence? What should be put in here?
Yeah.
Is that complete? Raise your hand.
Now, don't you need them?
Yes.
5.
Okay, so what's your name?
Thomas.
Thomas, okay. Remind me, okay, after this, remind me your name and team number. So 5
-5.
minus 5
-5.
minus 5
5.
5, right? So that's called the stiffness matrix. And is that complete? Is there anything else? Yeah, so the damping force. So the damping force would be add it because this is in series. So now I just copy the structure. So I delete this and
Replace the
plus
fives
sign. And so go ahead.
Replace the fives with twos.
Replace 5 and 2 by 2. Okay, so you
Yes,
have
by two.
2 minus 2 minus 2, 2. Is it correct? Is
Shouldn't
there
those
any
be-
error?
No, those need to be
Yeah.
derivatives.
Somebody, okay, somebody else, a new person. Okay, too many hands, so let me pick out. Yes. B prime, yes, the velocity. Okay, so that's it. That's an application of what we did last time, right? So very quick, let me remind. So Thomas, you go by Tom or Thomas?
Sure.
Tom?
Yeah, sure.
What team number?
5.
Team 5. And someone else, I forgot. David, yeah, team 2. Did I note you down?
Austin.
Austin, team 1. And Dylan, D-I-L-A-N.
YLA.
D-Y-L-A-N. Team 6. Okay, very good. So we are very active.
Very active. Very active.
That's more likely. I like that, you know. Okay, so let's with that, let's continue. I think I don't need my notes from last time, and let me save this to be sure that it's not lost. And so I'd like to bring up. So you have the hard copy of my notes now. Feel free to take notes on that, and I hope you like it. I mean, like to take notes on the hard copy and print out in the future. So this is section 53B. And this is a trick that I learned from a student in my finite element course recently, to make it into a window that exactly half the screen. Okay, so let me bring up the second, so that you can sort of follow where we are in the notes. And then I have a third window that I would zoom in, okay, later. So this is the table of contents, and we already went through this part, right? And we went through this page. Let me zoom out so that it fits. Here too. Okay. And we went through this page as well. Okay, and we're now here. Basically, last time we stopped somewhere here. Okay. Alright, so now let me zoom in. So this relation was the relation that we just applied. Okay, to provide the answer as a collaborative effort of the whole class. Okay, so here let's skip to this page and zoom in. Okay, so now you see, let me bring up this mask here to avoid overloading the information. So now you can introduce matrix variable, you know, just to write it in a compact form. So the matrix variable would be in boldface. Okay. If it's typeset, and if I had write by hand, I would have the underline, you know, the underbar under the symbol, because you know one cannot write in boldface by hand. So the boldface quantities are all matrix quantities. Okay, so here what we introduce here is the force matrix F that represents this column matrix. Okay, right now 2 by 1. 2 by 1 means 2 rows, 1 column. Okay, the stiffness matrix K, the superscript 1 in parentheses again designates the element number. Right, so that is this 2 by 2 matrix. Okay, 2 by 2. matrix, and this is 2 by 1. Okay, 2 rows, 1 column. And 2 by 2 means 2 rows, 2 columns. And the matrix D with the superscript 1 is the matrix of the displacement of element 1. The matrix C is the matrix of the damping coefficients. Okay, 2 by 2 matrix, and the matrix D prime, or the matrix of the velocities, dA prime and dB prime, right? So this is clear for everyone. If you have questions, please feel free to ask. Okay, and so here again, just what I said, the definition. And by the way, when I write in handwriting mode, let's say bring up my lecture notes here. Okay, so if I were to write this in matrix form or in compact matrix variable, then this matrix here I would write as F with the underbar, okay, or underline, and with the superscript 1. So the underbar underneath F, that represents a bold phase quantity, and same thing for all other matrix quantities. So in handwritten mode, that would be written as follows: F1, that's the force matrix of element 1 equal to the stiffness matrix of element 1 times the displacement of element 1 plus the damping matrix of element 1 times the matrix of the velocities, okay, of element 1. So let me move the prime out and put the so that's it. That would be how the relation would be written in handwritten mode, okay, handwriting mode. So you want to know both because you need to be able to interpret the typeset nodes, and also when you do your work, you want to have a way to write that you can distinguish between scalar quantities from matrix quantities. Okay, scalar quantities would be light face font, and matrix quantity would be bold face font. Okay, so that's so we already, so here I just basically rewrite what I said in words. Okay, force matrix, displacement matrix, stiffness matrix, damping matrix. One thing to note. What is the property of this matrix? If you look at this matrix here, what do you observe as a property?
Symmetric.
I hope someone in the class knows, so let me bring up the mask, and so that just focus on this matrix here. What can you say about the property, the mathematical property of this matrix?
Symmetrical.
Symmetric. Very good. What is your name?
File.
Kyle. Yeah, Kyle was sitting here, so now you're moving that. So I need to adjust team number.
6.
Team 6. Okay. Kyle said this matrix is symmetric. Kyle, could you explain to the class why is this matrix symmetric, or someone else can build on top of what Kyle said? Direct.
Yeah. So we take the determinant and have to do that one.
Take the determinant. Okay. Anyone else? Why is it symmetric? Kevin?
Kind of the layman's way is you can fold it over the diagonal, and
You can
it's
fold it
over the diagonal.
over the
And
diagonal
it's the same thing.
and looks the same. Okay, so what Kevin said is that, well, this is the diagonal, right? If you fold, then these two off-diagonal coefficients are the same. Okay, that's the definition of a symmetric matrix. Okay, so this coefficient here and these coefficients here are equal, and this is called the diagonal matrix. And So the concept of symmetry can be extended to when you have a matrix of size 1 million by 1 million. It's also the same. Okay? The coefficients of diagonal coefficients are the same. So here we take a simple example, but like I said, and keep pounding in the idea that the method that you learn here is applicable to very large systems. Exactly the same method. So let me note down, I think 3 people. Should so, Kai, team 6. Derek, what team number? 8. Team 8. Kevin, team what number?
7.
I think I already have
I'm up there,
so
yeah.
good. And I noticed on the screen. Sorry about that. Okay, very good. So yeah, let's move forward. Okay, so now we apply exactly the same idea to element 2, and now you see that once you understand the general formulation for the element AB, in which you cut off the support rather than include the support in the free body diagram. Okay, then the same concept applies here, where you have the cut at node B and node C, and replace at the cut the internal force at B belonging to element 2 and the internal force at C belonging to element 2. Note that the internal force FB belonging to element 2 is not equal to the FB of element 1. Okay, they're not the same. Why? Maybe somebody can say, let me write down so that maybe let me write on this here, because this is a quick note here. Probably I should write here so that you have some trace of what we discussed. What I was saying is that FB of element 1 is not equal to FB of element 2 and Y. Yes.
Because the spring and the damper and the spring constant and the damping coefficients of element 1 and element 2 aren't the same.
So are you saying that K1 is not equal to K2?
Yeah.
And C1 is not equal to C2? Okay, what is your name?
Kevin?
Kevin also, what team number?
Team 6.
Team 6? Okay, yes, Anderson.
So they're not equal. Are they also not opposite?
Right, of course. They're not equal in magnitude and not.
Okay.
Well, the sign, we don't really need to think too much about that, but the magnitude
Okay.
is clearly not the same. And yeah, if you look at the sign, you can also see.
Then would it be because there's a mass between the two of them?
Okay, Brandon.
Because displacement doesn't have to be the same for both, so
The displacement. Yeah, displacement is the same, but why the force are different? Yeah, like Anderson said, because there's a mass in between. Okay, and the mass. Why would the presence of the mass makes these two forces different?
Because the mass has its own force.
Inertial force. F equal ma. That's added in between. And we'll come to that, the free body diagram of the mass soon. Okay. So that's the preparation for like a look ahead. So the idea here is that you should not replace immediately the force FB of belonging to element 2 as equal to the force FB belonging to element 1. They are not the same. So that's why the notation is different. Okay, for FB and element 2. Now, this is the same element, right? In terms of the structure of the element, you have two elements in two components in parallel, the spring and the damper. The only difference would be the spring constant and the damping constant. Otherwise, mathematically, it's the same. You know, if you want the relationship between the force and the displacement, of course, the displacements now are dB and dc, and dB is also known as d1 because that's the first degree of freedom, and dc is also known as d2, the second degree of freedom. This is a 2 degree of freedom system. Okay. So because you know, mathematically or mechanically, this is exactly the same as element 1, then you have the same result of the force displacement relation, except that you need to distinguish that this is for element 2. Okay, so that's why the superscript in parentheses has the number 2. Of course, the coefficients of the stiffness matrix K2, stiffness matrix of element 2, and damping matrix of element 2 would have K2 and C2, so they are not equal to the stiffness matrix and the damping matrix for element 1, right? So that's the only difference. And again here, this is what I just said, where you have, this is the matrix variable of this matrix, okay, of the internal forces in element 2, and this is the displacement matrix of the displacements of the two nodes in element 2, node B and node C, and also in terms of using numbers, that would be D1 and D2. And so this is the stiffness matrix that has K2, the spring constants in element 2, and this is the damping matrix of element 2, and has the damping coefficients of element 2 in it. Right? And then, you know, this is the same story, so there's no need to repeat this story because now you are moving to the third element. This is the force displacement relation for the third element, exactly the same as before, with the exception now that you have number 3 in superscript in parentheses, designating that this force displacement relation is associated with element 3, right? And of course, the rest of the story is identical to the element 2, except that I would like to note here, you know, so element 3 has the node C and D. The internal force would be Fc for element 3 and F sub D for element 3. 3 is superscript in parentheses. dc, displacement at C, is also known as d2, the second degree freedom. And the displacement at point D, if you apply the boundary condition, that would be equal to 0. So that's what you want to keep in mind. K3 and C3 are the spring constants and the damping constants for element 3. Okay? And like what we did before, everything is identical to element 2, except that now the superscript has the number 3 in parentheses, designating that all of these quantities are associated with element 3. The stiffness matrix has the spring constants K3, again symmetric. And the damping matrix is also symmetric and has the damping coefficient C3. Okay? And they are not C1, C2, C3 need not be the same. K1, K2, K3 need not be the same. Okay. So now we see why, you know, that the force FB, the internal force FB of element 1 cannot be equal to the internal force FB of element 2 because of the presence of the mass, as Anderson said, and divide build on top. And the reason is because of this inertial force, right? F equal to ma. And look at the direction. Okay, now the direction of these two internal forces is easy to understand because when I look at when I perform the Euler cut, I assume the internal force in the elements are all in the positive direction. So by action and reaction, the internal force that element 1 acting on the mass would be in this direction, because the internal force that the mass acting on the element 1 was assumed to be in the positive direction. Makes sense to everyone? And what, Euler-Cut principle works as follows. However you assume the direction, when you match all the subcomponents together, the internal forces at the cut must disappear, right? So that's why you need to have action and reaction. So I think the meaning of the direction of the internal force is at B for element 1 and for element 2 in this direction, in the negative direction, is clear. Right? Now the applied force is again algebraically assumed to be in the positive direction. What it means is the following. If the value of F1 is negative, then physically the applied force is pointing in the negative direction. That's all. This is the same thing. The displacement is assumed to be positive in the positive x direction, and if you do the computation and if the result turns out to be negative, then it just means that the displacement is going in the negative direction. Now this is called the D'Alembert force. Anyone remember what the D'Alembert force? Who's D'Alembert? D'Alembert. Okay, so let me write the name. Maybe in red. Small d, capital A. Very famous person. So a French philosopher and mathematician who was among the first editor of the, who were among the editors of the first encyclopedia in the world, like Wikipedia. Wikipedia is a descendant of the work of D'Alembert and other French writers, and he's also a good mechanicist and mathematician. Now the D'Alembert force, everyone knows F equals ma, right? So if you have the mass, let me go back to this picture here. Right, so the mass here is assumed to move in the positive direction, okay? Because this is the displacement of the mass. So when the mass goes or when you accelerate your car, right, in the positive direction, you see, you can feel that your body is pushed back against the seat, right? And the force that pushes your body against the seat is the D'Alembert force. It has to be opposite the direction of motion. Makes sense? So there's a physical meaning, okay, to the direction of the D'Alembert force. So that's the setup. And now once you have the setup of this mass with the internal forces from element 1, the internal forces from element 2, the D'Alembert force, okay, which is mass times acceleration but with a minus sign, so it's pointing, when the direction is already pointing in the negative direction, you don't need to put the minus sign, okay? And then we have the applied force. So equilibrium, sum of forces equal to 0. That's how you do dynamic equilibrium. Okay, so let me zoom out a little so that I'd like to keep the free body diagram on the screen. Right, so you say sum of forces equal to 0. That's dynamic equilibrium, not static, because now you have the D'Alembert force. So you just do exactly as you did in statics, right? Sum of these forces. First you have the applied force, right? That's FB or F1. Okay. 1 is because mass M1, right? That's the first degree of freedom that corresponds to the displacement D1. And then you have minus, because we sum the forces in the positive x direction. So here you need to put the minus sign of the D'Alembert force, minus MB dv double prime. And the double prime is the acceleration of the mass at b. And then again, the positive direction is x, and these two internal forces pointing in the negative directions. You have minus fb of element 1 and minus fb of element 2. So clearly, fb at 1 cannot be equal to fb at 2. So we need to add to what Anderson was saying. The reason that fb of element 1 cannot be equal to fb of element 2 is not just due to the fact that you have the mass, but you also because of the presence of the applied force. Okay? Even if you do statics, even if statics meaning without the D'Alembert force, these two are not equal because of a non-zero applied force at B, at point B. Okay. Someone wanted to say something. Yeah, Kai.
I was just, could you go over how you get the direction of the D'Alembert for total calculus?
Yes. So the question that Kai posed is to go over. Let me zoom in so we have a bigger picture here. The direction of the D'Alembert force. Why is it pointing in the negative direction? Is physically, right? I think the best way is to think about physics. Because you don't even need to know Newton's law, and you can feel from your body, right? If you drive a car and you accelerate your car, when you, for example, from a starting point, right, you accelerate your car, you can feel that your body is pushed back against the seat. And so that explains why the inertial force is pointing in the negative direction. Okay. Think that the observer is your body, right? What are the forces that are applied on your body when the displacement or the acceleration is in the positive direction? So that explain, why if you are an observer sitting on the mass at B, these are the forces that you would feel. Okay. Assuming that the direction of motion is positive. Okay. So, all right, and and then once you have this, this is the key. This sum of forces equal to 0 here is the key. And I have 2 minutes. Yeah. Okay. So you have the. I should have distributed this. You can write a lecture. You should go with your team and write a lecture summary. You can also write questions. And this time I don't have your name here.
Team 1.
This team. Oh, okay. Team.
Your team 7, sorry.
Okay. I should open up. Each team only need 1 page. Yeah. So I actually. So could each team send a representative come up and pick up this? Well, let me have team 1. Where's team 1? Or maybe we start from team
7.
Team 9, team 7.
Wait, team 8. Sorry.
Team 8.
Team 8, team 8.
You don't remember your team number. Team 9.